The universe we see, the stars, the planets, even ourselves, all seem to obey certain rules. Laws of physics dictate how things move, how they interact, how they exist. But what if I told you there's a hidden world operating under a completely different set of rules? A world where the impossible becomes possible. This is the realm of quantum mechanics. In this hidden world, particles dance between states of being and non-being. They defy our everyday logic, existing in multiple places at once. They communicate instantaneously across unthinkable distances. It's a place where reality itself becomes blurred, and our understanding of the universe is challenged at its core. For decades, scientists struggled to reconcile this strange world with the familiar laws of physics. Einstein himself famously clashed with the implications of quantum mechanics, declaring, "God does not play dice with the universe." But the evidence is undeniable. The universe is far stranger, far more mysterious than we ever imagined. Join us now as we journey into the heart of quantum mechanics. We'll explore the mind-bending concepts that underpin this hidden world, from superposition and entanglement to the very nature of observation itself. Prepare to question everything you thought you knew about reality. At the heart of quantum mechanics lies a profound departure from the deterministic clockwork universe of classical physics. Instead of certainty, we find probability. Instead of fixed trajectories, we find a haze of possibilities. Imagine a single particle, say an electron. In the quantum world, this electron doesn't exist in one definite state. Instead, it exists in a superposition, a ghostly blend of all possible states simultaneously. It's like a coin spinning in the air, both heads and tails at the same time, until the moment we force it to land. This inherent uncertainty isn't just a quirk of the theory, it's been demonstrated time and again in experiments. The famous Double-Slit Experiment, for example, shows how particles can act like waves, spreading out and interfering with themselves, even though our classical intuition tells us they should behave like tiny marbles. This means the universe, at its most fundamental level, is not a collection of solid objects moving along predictable paths. It's a sea of possibilities. A quantum soup where particles shimmer in and out of existence, their fates intertwined in ways we're only beginning to understand. And if the idea of particles existing in multiple states at once isn't strange enough, quantum mechanics throws in another curveball: entanglement. Imagine two particles born from a single event. They are linked, not in a physical sense, but in a way that defies our understanding of space and time. These entangled particles share a destiny. Measure the state of one and instantly you know the state of the other, no matter how far apart they may be. This spooky action at a distance, as Einstein called it, has been experimentally verified. It suggests an interconnectedness at the heart of reality that challenges our very notions of cause and effect. It hints at a hidden web of connections that binds the universe together in ways we can scarcely comprehend. This is the world quantum mechanics reveals, a world where particles can be in two places at once, where information seems to travel faster than light, where our act of observation can alter the very fabric of reality. It's a world that can seem daunting, even unnerving, but it's also a world brimming with potential. By embracing the strangeness of quantum mechanics, we open ourselves up to new possibilities, new technologies, new ways of understanding the universe and our place within it. In the chapters that follow, we'll delve deeper into this quantum realm. We'll explore the groundbreaking experiments that have shaken the foundations of physics. We'll unravel the mysteries of superposition, entanglement, and the observer effect. And we'll examine how this strange, counterintuitive theory is poised to revolutionize our world in the 21st century and beyond. So buckle up. The journey into the quantum realm is about to begin. Our journey into the quantum realm begins with a fundamental concept that defies everyday intuition: superposition. Imagine, if you will, a single particle existing in multiple states at once. Not merely switching rapidly between states, but genuinely inhabiting all possible states simultaneously. This is the perplexing reality of superposition. Think of a light switch. In our classical world, it's either on or off, a binary choice. But in the quantum world, the switch can be in a superposition, both on and off at the same time. It's like a coin spinning in the air, existing in a blurred state of heads and tails until the moment it lands and we force it to choose. This isn't just theoretical whimsy. The consequences of superposition have been experimentally verified. Particles, like electrons, have been shown to exhibit wave-like properties, spreading out like ripples on a pond, existing in multiple places simultaneously, until the moment we try to pin them down. It's as if the universe allows for a multitude of possibilities to coexist, a ghostly dance of potentialities, until the moment of observation collapses this quantum wave function, forcing a single outcome into existence. But superposition is just the beginning of our journey into the quantum realm. For if the idea of a single particle existing in multiple states at once wasn't mind-boggling enough, quantum mechanics throws in another curveball: entanglement. Imagine two particles, linked in a way that defies our understanding of space and time, their fates intertwined in a cosmic dance. These entangled particles are no longer separate entities but rather part of a single, unified system. Measure the state of one particle and instantly you know the state of the other, no matter how far apart they may be. It's as if they communicate instantaneously, their destinies forever linked. This spooky action at a distance, as Einstein famously called it, has been experimentally verified time and again. Pairs of entangled particles separated by vast distances have been shown to exhibit this eerie correlation, their fates intertwined in a way that challenges our very notions of cause and effect. It's as if the universe has a hidden web of connections, a tapestry of entanglement that binds everything together in ways we are only beginning to comprehend. This interconnectedness suggests a deeper level of reality, one where the boundaries of space and time become blurred.
Entanglement is perhaps the most profound and mysterious aspect of quantum mechanics. It challenges our fundamental understanding of reality, suggesting that the universe is not a collection of isolated objects, but rather a web of interconnectedness, a cosmic dance of particles linked across vast distances. This interconnectedness has profound implications. It suggests that the universe is not a collection of isolated objects, but rather a unified whole, a cosmic dance of particles linked across vast distances. It hints at the possibility of non-local communication, where information can be transmitted instantaneously, regardless of distance. Imagine the possibilities if we could harness this power of entanglement. Instantaneous communication across vast distances, teleportation, the ability to manipulate matter at a fundamental level. These are just a few of the potential applications of this mind-boggling phenomenon. While we are still in the early stages of understanding entanglement, it has the potential to revolutionize our world in ways we can only begin to imagine. It's a tantalizing glimpse into the hidden workings of the universe, a reminder that reality is far stranger and more wondrous than we ever dreamed.
But here's where the quantum world takes an even stranger turn. This superposition, this ghostly blend of possibilities, this entanglement across vast distances, it all seems to hinge on a single crucial element: observation. The very act of observing a quantum system, of trying to pin down a particle's location or momentum, seems to shatter the superposition, collapsing the wave function and forcing the universe to choose a single outcome. It's as if the universe, up until that moment, was content to entertain all possibilities, but the moment we try to peek behind the curtain, it's forced to pick a card, to make a choice. This observer effect is one of the most debated and perplexing aspects of quantum mechanics. Does consciousness play a role in collapsing the wave function? Is there something special about the act of observation that triggers this collapse? Or is there a deeper mechanism at play, one we are only beginning to glimpse? These are questions that have plagued physicists and philosophers for decades, and their answers remain elusive. But one thing is certain: the observer effect lies at the heart of the quantum enigma, a constant reminder that we are not merely passive observers of the universe, but active participants in shaping the very fabric of reality. This notion, that the act of observation can alter reality, is perhaps the most perplexing aspect of quantum mechanics. It challenges our very understanding of the universe and our place within it. It suggests that we are not merely passive observers of the world around us, but active participants in shaping the reality we experience. Imagine a quantum system, a particle existing in a superposition of states, a blur of possibilities waiting to be realized. The moment we attempt to measure this particle's properties, to pin down its location or momentum, the superposition collapses. The wave function, that mathematical description of all possible states, collapses into a single outcome, a single point in space and time. It's as if the universe, up until that moment, was content to entertain all possible realities simultaneously. But the moment we try to observe it, to force it to reveal its secrets, it chooses one path, one outcome, and the other possibilities vanish into the ether. This collapse of the wave function is a fundamental principle of quantum mechanics, and yet it remains one of the most mysterious and debated aspects of the theory. What constitutes an observation? Does consciousness play a role? These are questions that continue to challenge our understanding of the universe and the nature of reality itself. But the strangeness of quantum mechanics doesn't end there. Consider the quantum Zeno effect, a phenomenon that seems to defy the very flow of time. Imagine being able to freeze a system in its quantum state, to prevent the wave function from collapsing, simply by repeatedly observing it. This is the essence of the quantum Zeno effect. By constantly measuring a quantum system, by repeatedly checking in on its state, we can prevent it from evolving, from collapsing into a single outcome. It's as if the act of observation itself freezes the system in a state of perpetual potentiality. This effect has been experimentally verified, demonstrating that the act of observation can not only collapse the wave function, but also, paradoxically, prevent its collapse. It's a testament to the bizarre and counterintuitive nature of the quantum world, where our very attempts to observe and measure can have profound and unexpected consequences. The quantum Zeno effect raises profound questions about the nature of time and the role of observation in shaping reality. It suggests that time itself, at the quantum level, may not flow smoothly and continuously as we perceive it, but rather in a series of discrete jumps, influenced by the very act of observation. To truly grasp the unsettling nature of quantum mechanics, we must confront the experiments that have shaken the foundations of physics. One such experiment, a cornerstone of quantum weirdness, is the Double-Slit Experiment. Imagine shining a beam of light at a barrier with two closely spaced slits. Classical physics tells us the light should pass through the slits and create two distinct bands of light on the screen behind. But with particles like electrons, the universe throws us a curveball. Instead of two bands, we see an interference pattern, a series of alternating bright and dark fringes. The strangeness deepens when we fire the particles one at a time. Yet the interference pattern persists, as if each particle somehow travels through both slits simultaneously, interfering with itself. If the double-slit experiment has left you questioning the nature of reality, prepare to delve deeper into the quantum abyss with Schrödinger's cat. Imagine a cat, sealed inside a box, its fate tied to a quantum event. Inside the box, a vial of poison sits beneath a hammer. A Geiger counter designed to detect the radioactive decay of an atom is linked to the hammer. If the atom decays, the counter triggers the hammer, smashing the vial and killing the cat. The atom exists in a state of both decayed and undecayed until the moment we observe it, and ultimately the cat itself becomes entangled in this quantum web, existing in a superposition of states both alive and dead, until the moment we open the box and observe the outcome.
Schrödinger proposed this thought experiment to highlight the absurdity of applying quantum superposition to the macroscopic world. Can a cat truly be both alive and dead until the moment of observation? The Copenhagen interpretation suggests that the cat exists in a superposition of states until the moment of observation. At that instant, the wave function collapses, and the cat's fate is sealed. Schrödinger's cat remains a powerful illustration of the profound conceptual challenges posed by quantum mechanics.
The double-slit experiment and Schrödinger's cat are stark reminders that the reality we perceive is but a thin veneer over a deeper, far stranger quantum reality. The universe, at its core, is a realm of possibilities, where particles dance between states of being and non-being. It's a reality where the act of observation itself plays a crucial role, collapsing wave functions and shaping outcomes. In the chapters that follow, we'll journey deeper into this quantum frontier, exploring the technological advancements born from this strange and beautiful theory. For decades, quantum mechanics remained largely confined to the realm of theoretical physics. However, in recent years, a quiet revolution has been brewing, a technological awakening fueled by the very strangeness that once baffled scientists. What was once considered esoteric and abstract is now finding practical applications in fields as diverse as computing, cryptography, and teleportation. By harnessing the bizarre properties of superposition, entanglement, and the observer effect, we are on the cusp of a technological revolution. Quantum computers, capable of solving problems that would take classical computers billions of years, are emerging from research labs. Quantum encryption promises unbreakable codes and a new era of cybersecurity.
Section 2. Quantum Computing, Reshaping the Boundaries of Thought. At the forefront of this quantum revolution stands the quantum computer, a machine that harnesses the bizarre laws of quantum mechanics. Unlike classical computers, which rely on bits, quantum computers utilize qubits. Qubits can exist in a combination of 0 and 1 simultaneously, allowing quantum computers to explore a vastly larger computational space. Imagine searching a maze. A classical computer would have to try each path one at a time, while a quantum computer could explore all paths simultaneously. By entangling qubits, we can link their fates, creating a system where the whole is greater than the sum of its parts. This interconnectedness allows quantum computers to perform calculations that would take classical computers billions of years.
Section 3. Quantum teleportation bridging impossibilities. Perhaps no concept captures the imagination quite like teleportation. At the heart of quantum teleportation lies entanglement. By entangling two particles, we create a link that transcends distance. Change the state of one particle, and the other instantly reflects that change. Scientists have successfully teleported quantum information across laboratories and even through fiber optic cables over distances of hundreds of kilometers. While teleporting humans remains science fiction, quantum teleportation has the potential to revolutionize communication.
Section 4. Quantum Encryption Secrets Woven in the Fabric of Reality. In an age of ever-increasing cyber attacks, the need for secure communication has never been greater. Quantum mechanics offers a surprising solution: quantum encryption. At the heart of quantum encryption lies the principle that observing a quantum system inevitably alters it. Any attempt to intercept or eavesdrop on this information would inevitably alter the photon's state, revealing the presence of the eavesdropper. Quantum encryption has the potential to revolutionize cybersecurity, protecting our most sensitive data from hackers and cybercriminals.
The journey into the quantum realm is not just a voyage through the strange and unknown laws of physics, it's also a journey through the annals of scientific history, a testament to the brilliance, curiosity, and sheer audacity of the pioneers who dared to challenge the very foundations of our understanding of the universe. From Max Planck to Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, the quest to unravel the mysteries of the quantum world has been marked by moments of profound insight and revolutionary discoveries. Their legacy is not just the body of knowledge they bequeathed to us, but also the spirit of exploration and the insatiable thirst for understanding that continues to drive scientific inquiry today. As we stand at the cusp of the 21st century, the quantum tapestry continues to be woven. The quest to understand the quantum world is far from over, with each new experiment and theoretical breakthrough adding new layers of complexity and wonder. Today, physicists are pushing the boundaries of quantum mechanics, probing the nature of entanglement, and exploring the potential of quantum computers. The quantum revolution is not merely a scientific endeavor, but a transformative force that is reshaping our world. The journey into the quantum realm is a journey into the heart of reality itself, promising to challenge our assumptions and expand our horizons. As we've journeyed through the strange and often unsettling world of quantum mechanics, from the ghostly dance of superposition to the eerie connections of entanglement, one question looms larger than all the others. What does it all mean? The implications of quantum mechanics extend far beyond the realm of theoretical physics. They challenge our very understanding of reality, of cause and effect, of the nature of observation itself. Is the universe inherently uncertain, a cosmic game of chance where the very act of looking shapes the outcome? Or are there deeper principles at play, hidden variables yet to be discovered, that will restore order to this seemingly chaotic realm? The answers, if they exist, remain elusive. But the quest to unravel the mysteries of the quantum world continues unabated, driving scientific inquiry into uncharted territories. Quantum computers promise to unlock computational power unimaginable just decades ago. Quantum encryption offers the tantalizing possibility of unbreakable codes, forever altering the landscape of cybersecurity. And as we delve deeper into the quantum realm, who knows what other technological marvels await, what new understandings of the universe and ourselves will emerge? The quantum horizon beckons, a frontier of infinite possibility and profound mystery. It is a frontier that challenges us to expand our minds, to embrace the unknown, and to confront the very nature of reality itself. The journey has just begun, and the discoveries yet to come may forever alter our place in the universe.